let's see here. Let's get back into PWM. So last time, if you remember, we started out, I left you with this timing diagram, or whatever you want to call this. Let's go, where is it at? Right here. This guy right here is what I kind of left us with. And we're going to see that, and if you also remember, this PWM peripheral is one of the reasons a lot of folks in the brushless DC world of motors, right? You call them either AC motors or brushless DC motors, this kind of thing. What motor we're going to use is called a brush style motor. It's one of the more inexpensive motors out there. Mainly, again, for the cost. The kind of the next step, if you're gonna, the lightest motor with the most torque and all that are these brushless DC motors that we're not going to deal with. I'd love to bring them in. They're just so much more complicated than a brush style motor. Maybe some year I'll get it done. Maybe they'll get it to a point where you can just plop one chip on and you can drive a motor. It's not quite to that point yet. There's quite a number of extra circuitry in there for driving these brushless motors. But for a brush motor, we're going to talk about it even today. There's a simple chip called an H-bridge that can be used to drive that. Now, multiple H-bridges can also drive the brushless style motors. Anyway, what I'm getting at is TI's real dedication to very precise PWM output is one of the reasons this processor is really popular. And TI has designed this chip, the 28 series chips, focusing a lot on this brushless DC motor technology. And so because of that, there are also, and I'm not showing you here, but as you look at the number of registers, we can even just look in this guide. Again, remember what I did is I made a condensed version. This right here, you would find this at the website right under here, PWM Tech Ref Condensed. Remember, there was that one document I showed you last time, there was like 2,800 pages in that one technical reference. And that was, describing all the different peripherals, and then a chapter of that was the PWM. Well, I took that chapter and I got rid of a lot of the things that we're not going to use. But still, if you look here, don't get scared. Look at all these registers as I go. Here we go. So all these listed down, we're not going to get into even half of all those registers. Okay, just so you know. But a lot of these things are, again, extra little tweaks that it's called EPWM. What's this crazy E? It just means enhanced. Well, it's been enhanced for 20 years. It's pretty funny. So the EPWM, that E's been there forever. But it's funny, I don't know why they don't do double E squared or something like that, because the PWM keeps on getting enhanced. So anyway, so all these extra registers are all the little tweaks that people have figured out that are needed, again, in this brushless DC world. Also some things in power supply design. They used, I understand they use these processors also in some really high precise power supplies / inverters, right? You have a battery backup system, right? And then you have to create an AC. You have battery, which is DC. For your computer, when you plug in your backup, battery backup, that unit is taking a DC battery and making an AC signal, right? To drive your AC cord of your PC. That's how that's backed up. Well, that also, this chip, these 28 series chips are used for that also. And so some of these settings and all this stuff are for that stuff I haven't got into. I don't know a lot of these registers and what they're actually for and all that kind of stuff. I haven't needed them, right? So I haven't, remember I said, I would have to, once I needed this thing, I have to sit down with this guide and read and reread and try to figure out what those settings are doing, okay? As I said last time, you read through a data sheet, hardly ever do you just read through it once and understand what's going on, All right, you read, try things out, come back. All right, anyway. So, but I will be showing you the registers we will be using. And so in this condensed ref, if you come down here, I only put the registers that we're going to be using. So there's this time, TB is timer base, is what that stands for. Controller. So this is the control register, time-based control register. So that's just some settings. The big one we're going to be using in there is what this thing called the clock divide, CLKDIV. And then, in addition, there's the counter register, right? We kind of talked about that last time. And here's a control register for the compares. In other words, down here, I do not list all the registers, only the registers we're going to be using. So that helps you a little bit to know which ones to focus on, too, right? So that's the idea of this condensed reference. Okay, now, again, what is the job when we think of generating a PWM, a pulse width modulated output, is what that's standing for. This little diagram is what you want to think about. And this is, yes, that's right. So, with these registers, you've got a couple registers, and they're called compare registers and period registers. The job of those registers, the job of the PWM, is to know when to pull the I/O line that it's in control of high, or when to pull it low. That's all its life is. Okay? It's just making this decision, when should that I/O signal be high and when should it be low. Okay? So when you, in this week, set up the MUX table, let's go back to that, see if I can get another page here. So when you set up to this week, go here to the MUX table, and we are going to be using, for example, PWM. Well, this week, which one? We'll be up here. We'll be using EPWM 12 right here, because this one's attached to an LED, or LED 1. So we're going to be setting this pin, GPIO 22, up as EPWM 12A. Okay? Once you do that, once you set the MUX for this guy to 5, instead of 22, 0, you no longer have control over that I/O pin in the sense of with GPA set register. If you say GPA set equals 1 for 22, it won't change. You no longer have control over that pin. Who has control? The PWM unit. Okay? And let's think of that PWM unit as, you know, really basic. You looking at your clock, your watch, maybe your stopwatch, right? And you have command over this I/O pin, and you're watching it. Okay, 3 seconds just went by. Pull that pin high, right? 2 seconds just went by. Pull it low, right? You see what I'm doing? The PWM has control to move that pin up and down by how you set up these period registers and the compare register. Okay? All right, good. So back to that diagram. Now, you know, again, TI could have just given you one option, but they want to make this PWM super versatile, right? Let's forget about PWM-B for a second. It's very similar, but let's just forget about it right now. We have, look at these events. This event right here where the PWM will pull the I/O line high. This is when the period, that ones that's not shown here is the TBCTR register. What is its job? Its job is just to count up by 1 every clock cycle that you give it. Right now, let's think of the clock cycle being every 50 megahertz. That's the fastest the PWM can clock at, is 50, well, yes, for us, it's the fastest it can clock at. So 50 megahertz. So every 50 megahertz, this value in the TBCTR goes up by 1, okay? Now, it's going to keep on going up by 1, boom, 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 until it reaches the TB-PRD value that we programmed that register to. Okay? TB-PT, all these, in this case, are all 16-bit registers. So the biggest value in TB-CTR would be 65,535. But normally it'll be smaller than that. Okay, so counter just counts up. That's what this is showing. Up, right? Until it reaches the period value. When it reaches the period value, it goes back to 0 and does it all again. This is very similar to our timer, wasn't it? In a sense, this is a timer. But now, what's happening in addition is not only is this going back to 0, we also are checking these compares. And let's just look at compare A. That's what that means right there. Compare A's value. So it's another register. It's similar to the period. Okay? If we're doing a PWM signal, think about it, compare A is always going to be less than or equal to the value in TB period. Because why? Again, it's deciding when the pin, in this case, we have programmed it such that when TB-CTR, when it gets reset back to 0, that event, or that action, we could call it, causes the PWM signal to go high. Okay? So that PWM was looking at its clock. Oh, it went to 0. Pull that pin high. Right? So that little unit. Pretty dumb unit. All he can do is look at a clock and pull a IO pin high and low, but still, he's doing it all himself. You don't have to do any of that in software. You just tell it once and it starts doing this. Then, as it's counting up, when it reaches compare A's value, let's say this was, period value was 10,000, maybe we put in the compare A value 6,000, right? So finally, the counter equals 6,000, so the PWM knows to set it low. Then again, it just repeats, right? Okay, and so if we keep those constant, if we keep compare A's value to 6,000 and period's value to 10,000, it'll stay at a 60% duty cycle square wave. Agree with that? Okay, good. Great. So now, notice here, well, whatever, you can change this. You could have, you're going to see that there's a .0 setting in the action control register. And you can set, when the TB-CTR equals 0, you can either tell the pin to go low or go high. So you have that control. Okay? You can, so, in this case, if we're going to make it work right, you have to do it the right thing. But in this case, we're setting it high. Same thing in this action control register. AQCTL is the abbreviation for it. There's a .CAU setting. There's this what's called compare A in up count mode. Okay, that you can then change to make the IO pin go high or low at that action if you want. So for example, if we found with our, I don't want you doing this, but one way to negate the PWM command is if your motor is spinning positive when you really want it spinning negative, you could switch these two actions here so that it's normally low and then high after the compare A. That would invert the PWM signal and it would make the motor spin in the opposite direction. I do not want you doing that in lab, but that would be a way to do it. Yeah?
Wouldn't that flip the duty cycle though too?
Sure would. And that's the idea. We'll talk about that. The 0 point for our PWM is 50% duty cycle. I'm going to get to that. So that good question. You're right. Because if it was a direction, anyway, if you're PWMing the speed, that would make it go slower, wouldn't it? Yeah. So good point on that. But I'll be explaining what I meant by that. Yeah.
Since there's two comparators, does that mean there's two PWMs?
That's right. Very good. So what's nice about this, a lot of times, especially in the 3-phase motor control and stuff like that, I was kind of surprised. Well, there is a compare C too on some of these processes. most of the processors only have compare A. I'm sorry, most of the PWM only have compare A and a compare B. But anyway, there are some that have a compare C, and in that case, that's perfect for driving three-phase motor control. Okay. What a lot of times what you find is you need. So what's happening in compare A, compare B share the same period register. So their carrier frequencies are the same. The rate at which they repeat is the same. We call that the carrier frequency. But you'll find the duty cycle can be varied between those two PWMs. Okay, so there's a unit called EPWM1, EPWM2, 3, all the way up to 12. Well, and maybe even higher. Each of those EPWMs have a compare A and a compare B. So in other words, they create two PWMs that could drive, each of them could drive a motor. And that's exactly what we're going to do. We're going to use EPWM1A and, 2A and 2B to drive our two DC motors, our two brush style DC motors. Okay? All right, good. So let's look in a little more detail here. So let's draw this out too. But first off, let's look at the registers just to see that. Sorry. If I go down here to Control A, let me find it here quick. There's the compare register. Close, I think. Am I lying? I'm lying. I could search, huh? I'd be smarter. Where's it at? Right here, right here. So, see, action control B and action control A. So, notice what you got, have the options. Remember I talked about the 0 option. Right here. So, here you go. When the 0 happens, in other words, when TB CTR equals 0, that's at the beginning of each period, you can either do nothing, you can clear the output pin, you can set the output pin, or you can toggle the output pin. Okay? You'd have to think about that a little bit. Most of the time, we're going to think about either clearing or setting that PWM pin, and not doing the do nothing. Actually, when we get to playing our tone on the buzzer, though, we will tell it. But that's next week. Let's not worry about that. Okay? We will tell it to do nothing on one of the actions. But anyway, so those are those settings that I was talking about. So you have 4 different settings you can make that I/O pin do. All right. So in our case, we're going to want to set the pin because we want at 0 we want the pin high, and it's going to stay high for its duty cycle and then go low, right? For its percent duty cycle, and then go low and then repeat. Okay. All right. And then for this compare A in up mode. Let's show you that. There's another setting. Oh, it's up here. Compare A CAU. That is, where did it go? Sorry. C on B. No, where is that? CBU? Where's CAU? Come on, Dan. All right, there it is. CAD is for when you're down counting. CAU is when you're up counting. Okay, this up-down thing. That's another thing. You can make the counter, TB counter, count up to a period value and then back down. Up and down. And when you do that, you can make little funkier PWM signals. I've never had a use for that either. So we will always be setting our PWM to up mode. So that just means it always counts up, up, and then when it gets to the period value, back to 0. Up, okay? So don't worry about this down count, all right? We're only going to be setting the CB up, CBU, and the CAU settings, okay? All right. Very good. So we'll always be counting up, and that's in a control register. You'll find that real easily in the lab. You'll set it up in up mode. All right. So those are those 2 things. Now, let's go and draw this a little better, or a little more vague, I guess. So our idea here is we would like to generate a PWM. Okay? That's not too consistent. But anyway, that's what we want to generate. what we have inside our DSP is, and let's just call this EPWM 2. Oops, 2. PWM 2. That's this unit. Okay? And its job, right? It's got the TB, CTR, 16 bits, TB, period, right? The PRD, and it's got, for now, well, let's put them both, compare A, and then for the second signal, we'll add to it, it's got a compare B. Okay, those are our 16-bit registers. And your job, first, is to set the carrier frequency. So, and I'll tell you what that is. Like for our motors, we're going to run at 20 kilohertz carrier frequency. For our RC servo motor, we're going to actually go really slow, 50 hertz. And we'll talk about that, okay, when we get to this little RC servo guy. Anyway, so what happens is, what rate is the TB counter clocking at? Okay, so I guess in a sense it's still inside the PWM. There is this 3-bit setting of what's called the clock divide. And it can divide down, slow down the 50 megahertz clock that's coming in. Okay? So if we go look at that clock divide, let me show you real quick. See if I can find it. Let me just search for it. Control F, CLK, DIV. There it is. So this little right here, we're not the high speed, we're just talking about these 3 bits. Bit 10, 11, and 12 of TB control. And again, you'll be able to change that with a bit field. If we go down here, these are our possibilities. It's just 3 bits, and those 3 bits can either be 00, right? 000 all the way to 1111. So we can take that 50 megahertz, okay, and we can divide it by all these possible values to 128. Okay? So we'll think about why we need that in just a minute, but this is important. The default is just divide by 1. But you could divide that 50 megahertz by 2, and TB CTR would be counting at 25 megahertz. You see that? Or we could divide by 4, and then TB CTR would be counting up at a rate of 12.5 megahertz. You see that? Okay? So we can slow down that clock. So if we go back to my picture here, so that's determining, this divide, right, is determining the rate that's coming into, and that TB CTR is counting at. Okay? Does that make some sense? All right. Then, of course, at whatever rate that is, TB CTR is, its life, again, maybe we made period, as I said before, 10,000. So its life is to start at 0, go to 1, go to 2, right? And when it reaches the period value, it'll go back to 0 and start all over again, won't it? And then our compare A is also a 16-bit value that maybe we set to 6,000 or whatever, like we said. Okay? And by just setting those 3 things there, setting this guy, setting this value, setting this value, that determines, the 10,000 determines the rate at which this is repeating, doesn't it? And the 6,000 determines the duty cycle. So to drive our motor, I'm going to explain in just a minute, the only thing we need to change, we want to keep the 20 kilohertz constant, if that's what we set it up as. To drive different torques to our motor so it spins forward, backward, and at different speeds, different torques, we're just going to adjust the duty cycle. So you'll see, like when we get our speed controller working later on in the semester, the only thing we'll change to change the speed is this duty cycle. We'll be changing the compare A register. And for the other motor, we'll be changing the compare B register, right? So we'll have those two compares changing, and those are our commands to drive the motor. Actually, though, you're going to write a function that kind of hides that all, and I'll explain that also either today or you'll understand it in lab too. So anyway, so we've got two signals coming out of this one PWM's unit to drive things. Right? Drive motors, drive heating coils, drive dim and LED like we're going to do initially. Okay? Good. All right. So let's think about this now. So now we know a little bit. Well, you know what? Let's take one example here. Let's say that, let's do this 10,000 and 6,000. Figure out what our carrier, this is not 20 kilohertz, okay? Let's figure out what it is. Why don't we just go ahead, let's do a clock divide by 4, just as an example. And let's figure out we know our duty cycle, because that's always a fraction of period. So that's all, we know that's 60% duty cycle, okay? Because that's a fraction of the PRD. But what is our carrier frequency? Let's do it quick. I didn't do this ahead of time, but let's see. So if our clock divide is a divide by 4, that's not a good divide, is it? That's modulus. So we're going to set it to divide by 4. That means it is set to 2, isn't it? Those bits, is that what it was? Let's see. Go back to this right here. See, if it was 2, we set those 3 bits to 2, 0, 1, 0, then it's a divide by 4. Okay, so that means what? That means our TBCTR is being clocked at 12.5 megahertz, right? So the period of each count is 12.5 million. So 12,500,000. Agree with that? Okay. Now, so that's the rate that TBCTR is counting at. So how long will it take it until it reaches 10,000? The amount of time is this period, isn't it? Times the period, the PRD value of 10,000. All right, so we can cancel zeros. So that'll be 1 over 12. Is that right? Does that make sense? My period there? So the rate, the carrier frequency of this right here is 1.25 kilohertz. Does that make sense? Okay. So you can imagine if we need to make it 20 kilohertz, the value that we put in TB period is going to be quite a bit smaller than 10,000, isn't it? Okay. Why do you think we need, what are you guys thinking? Why do we think we need this divide? Because we could have figured this out with a divide by 1 too, couldn't we have? And that would have given us a different carrier frequency. Why do we think we need this divide? Anybody have an idea? What if we wanted to do a really slow carrier frequency? Right? Like 50 hertz or something like that, like we're going to do in lab. You can't get 50 hertz. Yeah, let's think about that. Yeah, you guys think. Let's just go without a divide. What is the slowest carrier frequency we can come up with when there's no divide? Well, again, what is that? This is kind of the same thing we did in lab last time. So if clock divide, those 3 bits are equal to 0, that means we're dividing by 1, right? And so our biggest number that we can put in TB PRD is the 16-bit number, 65,535. Okay? And so 65,535 times our clock rate, right? The rate the clock's coming in. If we're doing divide by 1, that's 50 megahertz, right? So that's times 50 million. 1 over it, right? So those number of seconds, anybody have that in the top of their head? Let's see, calc. 5. Oh, I gotta get out of programmer mode, don't I? Scientific 65535 times, or divided by, shucks, let's go back. Can I do back? Yeah. Divided by what did I say? 50 million, right? 1 2 3 1 2 3. Okay, right there. That would be the maximum period or carrier frequency. 1 over that would be the carrier frequency of our signal that we could generate. That's a little bit slower than 1,000 hertz, right? 1 over 0.001 is 1,000 hertz, isn't it? So if I asked you to create a PWM signal with 50 hertz carrier frequency, that's a period of 20 milliseconds. That's close to 1 millisecond, right? You couldn't do it with a divide by 1. Is that making sense? You need to divide that clock to make it slower. Okay, so you'll be doing that in lab. You'll be thinking about that. Yes?
Could you repeat how you got the 12,500,000?
Oh, here?
Yeah.
For this one?
Yeah.
So, good. Up here, right? What happens is the 50 megahertz can be divided. I chose, for this example, to set it to 2.
Okay.
When it's 2, that's a divide by 4. Did that make sense?
Yep.
Yep. And so 50 megahertz divided by 4 is 12.5 meg.
Thank you.
Good. Excellent. All right. So now, all right, it's going to take, now you'll have to do some stuff in lab. Now the cool thing is, not only are we going to set all these parameters in our registers, we're also going to look at this scope, this square wave on the scope. Okay, so you're going to be able to see this duty cycle changing. So when you get in the lab, I think it'll even make more sense as you start playing around with these numbers. Okay, good. Now, let's say we understand the PWM. How will we use that PWM? Let's do that for the last little bit here in this lecture. Well, just think about it. We have our LED circuit, right? So we've got our resistor. Let me see. It's 3.3 volts through our 1K ohm resistor, and then that goes through our LED. You can draw it like this. Oh my. Like that. To ground. No, I'm sorry, not to ground. To our I/O pin. What am I saying? That would just always be on, wouldn't it? So we've got this inverter, that chip you signed it on, the 7404, and then here's your GPIO. So for example, GPIO 22 is 1. So in other words, whenever we set this pin high, so whenever this is 3.3 volts, the inverter inverts that to 0 volts, right? And the LED turns on. Agree with that? Because the voltage on this side is higher than the voltage on the other side, the LED turns on. When we have the I/O pin low, then this is 3.3 volts and the LED is off. So 3.3 is on, 0 volts is off for our circuit on the board. Great. Now what would happen if first off, what happened if this is 1 second? The time on and time off. What would you see?
It would just blank.
Bang, like that, right? Now the key is, what if we speed up this period? What if we make this, as we said, 20 kilohertz? That's what we're going to do in lab. That means it's going to be 50%, for 50% of the time it'll be on, and that'll be for 50 microseconds. That's 20 kilohertz, is 50 microseconds. And off for 50 microseconds. What's the LED going to look like? Dimmed. It should be 50% as bright as always on. Right? And then as we change that duty cycle, it'll get more and more dim as it gets lower in duty cycle, and then gets brighter, and then so we're actually going to write a program that starts it out at dim, 0% duty cycle, and gradually increase that till it gets all the way bright. And then we're going to decrease it, and then increase it. So we kind of fun seeing that LED brighten and dim as we change its duty cycle. Right? Good. Okay. So that's what we're doing with the LED. And that's one way to do that. We'll also give you, I'm going to have you pulse width modulate that at a carrier frequency of 40 hertz. What's the fastest your eyes can see? Like 30, something like that. You can see 40 almost. And when you do something at like that 40 hertz rate, it makes you almost get a little sick, doesn't it, if you're seeing frequencies like that. So you'll be able, we'll do that with the LED, and if you kind of move it like this, it'll kind of look kind of funky. Anyway, you'll see that your eyes will be playing tricks on you, that you can kind of see it blinking at 40 hertz. But anyway, we'll do that in the lab. It gives you the values. Okay, now, the important one is our DC motor. We'll talk about the H-bridge another day also, but we have this chip called A4793. This was the hardest chip for soldering, that little fat one, that little fat surface mount chip that we put on there. That is our H-bridge chip that drives our motors. Okay? Let's not get into all the details of this, but it's got motor plus out and motor minus out. And you draw your DC motor something like this with its brushes and its stator and rotor and all this great stuff. You usually see them like this. Well, this guy, the inputs to this are, one, its enable line. Okay, and that bar over means it needs to be low to be enabled. And then it also has a direction line. Well, the enable line, you guys remember when I was playing with your motors, testing them out, there's a little slide switch you soldered to your board. That's the enable. By slide switching that, you're enabling or disabling. So that's just a manual switch. So that's how you enable and disable the motor. The way you drive the motor is by pulse width modulating the direction line of the motor. Now let's think about that again real quick. If this again was 1 second, really slow, the direction, what would that do? When the way this direction pin works is if the signal to the direction pin is high, it tells the motor to spin in the positive direction with full torque. If the direction line is low, it tells the motor to spin in the negative direction with full torque. So if we're doing that every second, what's the motor going to be doing? Spinning up and then spinning down. Spinning up, spinning down. All right? Or spinning negative. Not down, but negative. Does that make sense? All right? Because we're doing it so slow. And the time constant of the motor is in, 300, 400, 500 milliseconds. Half of a second. So it's actually going to move. But now, what if we change this period again? And we get it into the 15 microseconds, the 20 kilohertz range. What's the motor going to do when it's at 50% duty cycle? What do you think? Yeah.
It'll stop.
It's zero, exactly. So in other words, you're telling the motor at a really fast rate, hey, go forward for 50% of the time and go negative 50% of the time. Since it can't react to that, it's the same equal on and off, it's just going to sit there. Due to the time constant, the electronics, the inertia of the motor, all that, it's transfer function. You would see the same kind of thing if you took a transfer function in Simulink, hit it with a square wave like this, on off, you would see that the output of that transfer function wouldn't move. The time constant of the system filters that square wave out, in a sense. Okay? So, now what do you think happens when you change the duty cycle? Let's say you're on for 75% of the time, off for 25% of the time. Which direction is it going to spin? Anybody? Yeah.
Forward.
It's going to spin forward because it's being told to go forward 75% of the time. It's being told to go negative direction 25% of the time. So that again, the time constant of the system filters that all out, and it actually, the motor sees that as a command to drive 50% of its torque in the positive direction. You get the 50% part, right? Because 50% duty cycle is 0. Anything greater than 50% we're telling it to go positive with positive torque. Anything less than 50%, we're telling it to go in the negative direction with negative torque. Okay. So as we change that duty cycle, we can command the motor to spin or command the motor to generate a torque. Now it is a little noisy doing this spike. There is current going through the motor because the motor's time constant, the electronics, is much faster than the time constant of the whole system, the inertia and all that. So this does create a little bit of interference sometimes with your systems. So you do have to watch that. And so there are linear amplifiers out there that drive linear current without this square wave stuff, but they're so much more expensive. This is the low-cost method, and you just have to know that this produces a little bit of electrical noise that you got to watch out for. And anyway, that's the way that's done. But okay, so we're going to do that. We're going to set this up. Now, what we're going to be doing in lab too, just to finish out this lecture, I'm going to have you make a function something like out PWM, I forget what I asked you to be the name of it, 2A. Let's just say that's what it is. And this will drive one of your motors. Okay? There'll be an out PWM 2B also for driving your other motor, or whatever I call the function. Now what I'm going to ask you to do is pass a number, a float, float, and call it maybe command or whatever you want to call it. And actually, the range of this command, I'm going to ask you to be of range between -10 and 10. Now, the reason for this is kind of my preference. When I started doing control here at U of I, and it's still somewhat of a standard, the standard voltage output that you drive motor amplifiers with, especially years ago, was a range of -10 volts to 10 volts. That was a standard DAC out range, digital to analog output range. So when I came to start doing, instead of DAC outputs to drive my motors, went to PWM to drive my motors, I stayed with the same range. Okay? Some companies you'll see, like National Instruments, a lot of times uses -1 to 1. Okay? But for this, why? It actually really is neat. The PID gains, when you use this range, are similar for when you drive PWM to when you drive DAC voltage. So it keeps the PWM, it keeps the KP, KD, all those values of your PID loop very similar across platforms, which is kind of neat. There's little differences, but not huge ones. Anyway, so that's kind of my justification. And what we're going to do in lab is we're going to make -10. You're going to see that, and when you see -10, you're going to output 0% duty cycle. When you input 0, you're going to be outputting 50% duty cycle. When you output 10, you're going to be outputting 100% duty cycle. And then, of course, it's linear within that. Anyway, okay, good.